Okay, so we are going to carry on with looking at solubility equilibrium today. And what we're going to focus on is a situation where we have something called a common ion. So I'm just going to go through the first little bit here and try to diagram out what's happening, and then we will apply it to some of our problem solving with KSP. So this is a situation. If we were to mix a solution with another one, which has a common ion, so what that means is that you have two solutions and they each contain one of the same ion. So for example, we mix silver chloride with silver nitrate. So what they have in common is silver. So they're each going to, when they dissociate, they're each going to produce Ag plus ions. Okay, so what happens when you mix these two solutions with a common ion, the silver ions from the silver nitrate actually cause the solubility of the silver chloride to go down. Okay, so an important thing to note about these two solutions, silver chloride and silver nitrate, is that their solubilities are very different. So when we mix, anytime you come across a problem with a common ion, you always have one of your compounds is highly soluble. So if you were to check your solubility rules, silver nitrate is very soluble. So let's just put highly soluble. And the other one has very low solubility, kind of like the ones we focused on in the last lesson. So AgCl has low solubility. Okay, so why does the solubility of AgCl go down when these two things are combined? So let's try to look at this, and this all ties back to Le Chatelier's principle. Okay, so if we have a beaker here, so here's our beaker. Okay, so, and it doesn't matter which gets added to which, like which one was in the beaker first or what. The whole idea is that they come together at some point. So let's say we start off in our beaker with the AgCl, the silver chloride. Okay, so because it has very low solubility, I'm going to draw it like a little lump at the bottom of the beaker. And the reason for that is because very little of it actually dissolves. Okay, however, we do know it's not completely insoluble. You still get some silver ions dissociating. So let's just put Ag plus, and you still get some chloride ions also dissociating. So I'm just going to show two of each. Sorry, this is going to be a little bit messy. And what happens is we know this will reach an equilibrium point. So that's kind of what we looked at last time. So for every silver ion leaving, another one will enter back into the solid, right? So they reach an equilibrium point. Okay, so one leaves, one enters, and so forth. So you kind of keep those concentrations constant once the equilibrium has been reached. Now, I wonder if I can fix this so it's a little bit easier. Try a different sized line so it's less ugly to look at. Still pretty ugly, but oh well. Okay, so this is what's going on. Not much is dissolving, but you get a little bit of dissociation, and then you get an equilibrium point reached. So now let's add to this the AgNO3. And this is very soluble. So this is going to completely dissociate. So what's going to happen is you're going to get, your silver ions and your nitrate ions, and you'll have lots of those. So all of a sudden, what we've done is we've increased the amount of silver ions. We had already some silver ions in solution from this. Now we've just added more. The nitrate is basically just a spectator. It's just going to hang out and watch what's going on. So we no longer have equilibrium now, right? So now we've just increased the concentration of silver. So an equilibrium has to be reached again. So in order to reach a new equilibrium, what happens is this amount of silver has to decrease, right? So it's just like Le Chatelier's principle. If you cause a stress to the reaction, you're going to have to counteract that stress to get back to equilibrium. So we have to do something about this excess silver. So what happens is that excess silver actually joins back on to the silver chloride. Okay, so it precipitates out into the silver chloride. Okay, so you get some silver going in and joining this solid at the bottom, and that causes a decrease in the silver ion concentration. However, if you're having silver join on, you also have to have chloride join on, right? Because for every one silver ion, you need a corresponding chloride ion. So chloride also has to join back on. So the end result is you get more AgCl forming. So you get a larger amount of the precipitate, and if you have a larger amount of the precipitate, that means it's less soluble. There's less of it dissolved or dissociated in the water. Okay, so therefore, its solubility decreases. Okay, you've got an increase in your Ag, whoops, the concentration of the silver increased, and it's going to cause the chloride ion, geez Louise here, to decrease, right? Okay, so remember the KSP value is constant. So these are the two things that the concentration of silver and chloride are the two things that you use to calculate KSP. So if you get an increase in silver, you're going to have to get a decrease in chloride. And that's also not just mathematically, but logistically, if this silver is forming onto the precipitate, you also need a matching chloride every time a silver joins on. So that's going to cause the amount of chloride ions that are dissociated to go down. Okay, and this is going to continue to happen until a new equilibrium is reached. So very messy diagram, but hopefully my explanation helped you understand why this occurs. So let's just look at, we'll write out the dissociation reactions for both. So this is something, I'm having a lot of trouble with the pen here today. This is something we've done a lot. We show the solid silver nitrate breaking up into silver plus ions and nitrate, negative ions. And the silver chloride would do the same thing, break apart. Okay, so plus and chloride is negative, and that's what it looks like. So this next little bit just sort of talks a little bit about what I tried to explain here with the diagram. So the silver Ag plus concentration of ions is higher than normal, than it normally would be at equilibrium for a silver chloride solution. The value of KSP, though, for AgCl is a constant, so it can't go down, or it can't go up or down. right? It can't change. What happens to counteract the increase in concentration of the AgCl plus is the concentration of the chloride ions, and therefore the solubility of silver chloride goes down as well. Okay, and that's what I kind of showed here. If this is increasing, this has to decrease, and what's happening is we're getting more of this precipitate forming, which means it's less soluble. So this is predicted by Le Chatelier's principle. If the concentration of Ag goes up, so if we add more of this, we've got to use that up. So we're going to shift to the left, which means more of this forms. So if the concentration of silver ion goes up, then the equilibrium shifts to the left, causing more AgCl solid to form or precipitate. The chloride ion decreases until a new equilibrium is established. Okay, so eventually it will reach that equilibrium point, and then all concentrations will stay constant. So note that the solubility of an ionic compound goes down when it is mixed with a solution with a common ion. And in particular, the one that solubility decreases is the one that has very low solubility to begin with, the one that would form a precipitate. So what do we do with this concept in terms of solving problems? How does it change how we do our calculations? So here's the scenario. Calculate the solubility in moles per liter of silver chloride in a 6.5 times 10 to the negative 3 mole per liter solution of silver nitrate. The KSP for silver chloride is this value here. Okay, so let's just go through it step by step, but I'm first going to kind of draw out the scenario. Okay, so here's our beaker. Okay, what we have here in the beaker is I'm going to show the silver nitrate. Okay, now the silver nitrate, anything with nitrate is highly soluble. So this is our highly soluble, which we already actually identified earlier, and this one is low solubility. Okay, so it's the one that's not going to, it's going to form a precipitate at the bottom. Whoops. Okay, so here's the solution, and we're told that this solution of silver nitrate has this concentration. So we've got a 1-to-1 ratio here, right? For every one silver ion, there's one nitrate ion. So that means that the concentration of silver ions is 6.5 times 10 to the negative 3, and same with the nitrate. Okay, so we're bringing in the silver chloride into a solution with a particular concentration. So when we add in the silver chloride, and I mean, really, this could happen in either direction. The big idea is just that these two are getting mixed. Then we're going to see what happens to this silver chloride. Okay, so let's write out the dissociation equation for silver chloride. That would be always your first step in any of these problems. Okay, and the KSP. So remember, we never include the solid, we just include either gases or aqueous. In this form, it's aqueous. Okay. So from there, what we're going to have to do is we're going to have to make our ice table. Okay, and we're going to work through that based on what we know already. Okay, so I have silver and chloride. Okay, now in the last lesson, when we did an ice table, we always started with a concentration of 0 for both products, for both ions, right? Because at the beginning of the reaction, before any dissociation has occurred, neither of these would have a concentration. But now we're in a different scenario. We're adding into a solution that already contains silver ions. So this, okay, so we already have a concentration of silver ions in the solution. So we have to use our initial concentration as that concentration we were told in the question, right? So we already diagrammed that out on the last page, and we showed that the concentration of silver ions is actually 6.5 times 10 to the negative 3. Okay, the chloride ions, on the other hand, there were no chloride ions to begin with, right? This would start at 0. So it's only the common ion that has a concentration. Okay, when it comes to the change, we're going to use x's just as we did before. And remember, the x value reflects the stoichiometry of the equation. So we have a 1-to-1 ratio of silver to chloride. So these are both going to increase over the course of the reaction. And we could represent that as just plus x. So when we go to show at equilibrium, this one is going to be 6.5 times 10 to the negative 3 plus x, and this one's going to be x. Okay, so now we can kind of, for the most part, carry on as we normally would. So the only real difference here is that the starting concentration is not 0 because there was already some silver ions in the beaker. Okay, now the nice part about this is instead of dealing with this multiplied by this to solve for KSP, because AgCl has such a low solubility, X, which is the concentration of the chloride ion, would be very, very small, right? So this is already a small number. The X value is going to be even smaller. So we can actually just say that that's like a negligible amount. It's so small that it's going to round to this value anyway. So we can simplify the equilibrium concentration of the silver ion to just simply this amount. Adding this little bit of X is going to be so insignificant that we don't even need to factor it in. So we're going to just write out our KSP. Okay, and we were told in the question that the KSP is equal to this value. Okay, now instead of writing this whole expression, I'm simply going to write it as 6.5 times 10 to the negative 3. And for chloride, I'll just put X. Okay, so now that's a lot easier to solve than it would have been. So all I really need to do here is divide by this value on both sides, and then I'll know what X is equal to. Okay, so when you calculate that, you get that X equals 2.8 times 10 to the negative 8. Okay, so from there, what is the solubility then of the silver chloride? Well, because it's all a 1-to-1-to-1 ratio, whatever X is equal to is also what the solubility of the silver chloride is equal to. So I'm just going to write this out. The solubility of AgCl is 2.8 times 10 to the negative 8 moles per liter. And we can also show that in grams per liter. if we convert. Okay, so we want to put moles here, grams here, in 1 mole. So this would be the molar mass of the silver chloride, which is 178.77. So then moles will cancel, and it works out to 5 times 10 to the negative 6 grams per liter. So that shows the solubility in 2 different units. All right, let's do a couple more examples, and then you can try some on your own. So example 2, what's the molar solubility of the PbCl2 in a 0.2 mole per liter solution of NaCl? Okay, and notice that it's got aqueous here. This is the highly soluble substance, and this one is low solubility. So this is the one that's going to precipitate, and the one we're going to get an increased amount of. Okay, so let's write out PbCl2. We'll write the dissociation reaction. We've got lead 2 plus and 2 chloride ions. Okay, so I am going to make my ice table first. Okay, so what's the common ion here? We've got lead 2 chloride and sodium chloride. So chloride is the common ion. So that means when I go to add this PbCl2 to this solution, there's already chloride ions in that solution, dissociated in that solution. So I don't start at a concentration of 0 for chloride. I start at a concentration that is given in the question. Okay, so let's just actually, because this one, it's not a 1-to-1 ratio here. So let's actually draw this out so that we get our concentrations correct. Oops. Oh, whoops, sorry. This part isn't a 1-to-1 ratio, but the NaCl is a 1-to-1 ratio. Okay, so you've got sodium and chloride, and because it is a 1-to-1 ratio, if the concentration of sodium chloride is 0.2, then so is the chloride ion. Okay, so when we fill in our ice table, we've got no concentration to start with for the lead, and we've got a 0.2 mole per liter concentration for the chloride. Okay, sorry, I was getting myself confused there. It's this dissociation that does not have a 1-to-1 ratio, but that factors into the KSP shortly. Okay, so the change is going to be plus X, and for chloride, because there's 2, it would actually be plus 2X. Okay, so this one becomes X, and this becomes 0.2 plus X. So when I write the KSP, I've got lead times the concentration of chloride, and the chloride would have to be squared. So I'm going to put in here my KSP value, which is 1.7 times 10 to the negative 5. Lead, I said, was X, and again, I'm always going to eliminate this X here when I do these problems because this X value is so small. I'm just going to simplify that one to 0.2. Okay, then I can divide by 0.2 on each side, and that gives me my value for X to be 8.5 times 10 to the negative 5. Okay, so if it's asking me what is the molar solubility, well, if X equals this, you can see this X is equal to lead, the lead ion, and the lead ion and the lead 2 chloride are in a 1-to-1 ratio. So X is the molar solubility of the lead 2 chloride. So the molar solubility of PbCl2 is 8.5 times 10 to the negative 5 moles per liter. All right, one more to try. So here we have silver iodide, and it's getting added to a solution of sodium iodide, and that sodium iodide has this concentration, 0.274 molar. So let's dissociate the silver iodide. Okay, and we'll make our ice table. Silver and iodide. So our common ion here is the iodide ion. So if we're adding the silver iodide to the sodium iodide, there's already a concentration of iodide ions in solution, and that concentration, because this is a 1-to-1 ratio, is the 0.274. So I'm going to put that in here, whereas the silver, there's no silver in the beaker before I add this, so it would start at 0. We're going to go plus X, so we get this. Okay, so our KSP would look like this. Okay, and our KSP value is 8.52 times 10 to the negative 17. And silver is X, and iodide, we're going to eliminate the X and just put it in as 0.274. Okay, now I'm going to divide on both sides, and I'm going to get X is equal to that. So that equals 3.11 times 10 to the negative 16. So the solubility then is, if X is equal to this, then it's also equal to the solubility of silver iodide. So the molar solubility of silver iodide is 3.11 times 10 to the negative 16 moles per liter. Okay, I just realized I missed one little step up here. I had the chloride ion squared, but then I didn't square it here. So let's fix that. Sorry about that. So that's going to change this a little. Okay, so instead of dividing by 0.2, it's actually dividing by 0.2 squared. 0.2 squared is 0.04. So I should have divided both sides by 0.04. So that would actually calculate out to 4.25 times 10 to the negative 4. Okay, sorry, you'll have to go back and correct that little mistake. Okay, so that should all be good now. So what I want you to work on is I want you to work on worksheet 3 and the common ion questions. They'll be attached in today's post. So the worksheet 3 has more of the KSP problems that we tried in the last lesson, and then the second part of it is more focused on this common ion effect.